Okay, let's deal with a relative velocity problem here. So a pilot must fly a route of 20 degrees south of east at a ground speed of 200 meters per second. There's a wind blowing at 75 meters per second, 30 degrees north of east. Calculate the pilot's airspeed and heading. So first we have to decipher what this means. All right. So presumably, he's got to fly 20 degrees south of east. Maybe, his starting city is here, okay, and his ending city is, say, somewhere down here, okay, so this is his destination. And so if we want to show that displacement, he's going to fly somewhere like that. And what we might realize here, just give me a second, draw some stuff. This is 20 degrees south of east. Okay. We don't know how far away this is, but planes give a predicted arrival time, and in order to get there, we just understand that he's got to have a velocity of 200 meters per second along this route. Does that make sense? So we call this the ground speed because this is the geographical overground direction that we need the plane to travel on. Okay? If there were no wind, the pilot could just fly straight there, no problem, right? Just go straight there. However, there's a wind blowing at 75 meters per second, 30 degrees north of east. So I'm going to add that in. So 30 degrees north of east. So first, let's give ourselves a guidepost here. And since we add our, that's not straight. Since we add our vectors tip to tail, we'll put it over here, and we'll add that wind vector on there and see what it would end up doing if we did not correct. Okay, so we'll put here, this here is just a guidepost, and we said that then that the wind is blowing 75 meters per second, 30 degrees to the north of east. Okay, so there's east, and we're going about 30 degrees to the north of at about 75 meters per second. Okay, so just move this out of the way. I'm going to write some stuff in, and we'll add in our guidepost again here. Oops. Oh, for goodness sake. It's like every video I mess the background up somehow. It just never fails. Okay, so the wind is here, 30 degrees. Oh, goodness sake. You're better than this. 30 degrees. Oh, I'm going to get there. I could do this. I've done it before. It is possible. Huge challenge today. Okay, there we go. 30 degrees. So, let's just pop these guys out of the way. They're kind of annoying. Okay. So, what we're saying then is if we did not correct for the wind, right? If we did not correct for the fact that we have a wind, and we just aimed our plane at this heading, straight at our destination. My whole destination moved. Go back to your destination. I don't even know. Okay, you would end up, right, flying a route over here, okay, and this would be the velocity vector. It would be up over here somewhere, okay? So that's no good. You don't want that. So what we're going to have to do is we're going to have to account for, or we're going to have to correct for that vector. So let's just do a little redraw here, okay? And so in order to correct for this, we're going to need to account for the fact that the wind is really, in real life, blowing up and to the right. So we're going to have to aim our plane down here, okay? So our plane's going to aim down there. That's the heading that we're going to have to actually take here. So when you think about it, what's going on is going to be this. So I just grab this and I put it here, okay? And I grab this, put it here. What we should see is, if I fly my plane down here, the wind will add to that vector, and the resultant vector will be the direction I want to travel. Okay, so the result of where I fly, where I aim my plane, and the velocity that I have, plus the wind, should put me on the route that I require. All right, so let's label these vectors because now we've got to use the component method in order to find values for them. Okay, so here's vector A. All right, this is what we want to end up at. So this was 200 meters per second, and it's 20 degrees south of east. And now our B, our flip vector, the vector that we're accounting for, we're actually doing a vector subtraction here, is 75 meters per second, and it should be 30 degrees south of west. It's 30 degrees south of west now. So these are the two vectors we now have to add up such that we can figure out where we're going to actually aim our plane so that the wind blows us back on the course we need to take. Okay? So to sort that out, 200 meters per second, 20 degrees south of east, plus 75 meters per second, 30 degrees south of west. Okay, so we're going to sum these vectors, and the way to do that is to, oh, for goodness sake, the way to do that is to separate them into vector A and vector B. So here's A, we know it's 200 here, and that's meters per second, and that it's 20 degrees south of east. So what we're going to pull off of here is we're going to pull off the, this is vector A, the AX component, which is going to be 200 cos 20 degrees, and that's going to be in the east direction. And then we're going to grab the Y vector off of here, which is going to be 200 times the sine of 20 degrees, and that's in the south direction. Okay. I like to just give myself a little note so I can do that. Okay, and then over here, this is vector B, and this is 30 degrees here, and this is 75 meters per second. We know that the By value is 75 cos 30. All right, and that's not Y, that's X. And the Y is 75 sine 30 degrees. And this one is going to be to the east, and this one is going to be to the west. No, it's not. The south. And this one is to the west. Holy smokes. I can do this. We're good. We're good. This one's to the west. Sorry. Okay, so you can just kind of like gather up your values here. Here's your X's. Here's your Y's. Okay, just keep in mind that the direction matters. So we're going to call east positive here and west negative. Okay, since these are both in the south direction, we know they're going to sum up and you're going to go farther south in both of them. So south plus south. So I didn't bother to put them negative, but if you're someone who needs south to be negative, then they can both be with a negative value. Okay, and so let's go ahead and solve values for this. Okay, so here's the first part. This works out to be 187.9 in the easterly direction. This is 65 meters per second, but in the westerly direction. That's this guy up here. So summing those together, you get 122.9 in the easterly direction. That's your net change in the Y direction, and here's your Y net. So we've got AY plus BY. Just solve these values and add them in. Okay, so there's our Y's, both in the southerly direction, so 68 and 37.5. And you get 105.5. And that's in the south. Okay, and so now our last step then is to find the new right angle vector. Okay, so it's east. I don't like that. Or that. It's east. Okay, and south. Values would be 122.9 Notice that it's less than 200, which makes sense, and 105.5, and we need to find this and this, okay? So we're going to find the sum of that as the hypotenuse of a right angle triangle. And then the angle, theta, is found as the inverse tan of the opposite over the adjacent. So this gives you about 41 degrees here. Okay, so you write the final answer then is that the plane must have an airspeed of 162 meters per second, 41 degrees south of east. Okay, so if you want to like just have like that final sort of overview of what actually happened here, you aim your plane here. That's 162, 41 degrees south of east. The wind blows like this. Okay, you end up flying where you wanted to fly all along, right? You aim your plane there, the wind blows you there, you fly along this route, okay? And that'll give you 200 meters per second, 20 degrees south of east. And there's that 75 meters per second wind that we had before. It's actually, and this isn't drawn to scale, this is only a 30-degree angle, but I've drawn a little bit harsher angle than I should have, okay? So there you go. Okay.